Welcome. This is our second handout on the properties of cosets. And today we are finally going to get down to the business of what all this says about the sizes of certain subgroups and the sizes of cosets, all in relation to the size of the parent group G. So you saw this phenomena happen in class and you saw it on the last handout. So I think now it's time to actually prove it. So the result of proposition 1 is the first important one, and it just says what you noticed before, which is let H be a subgroup of G, and suppose you had any element of G, call it little a. Then if you look at the coset AH in relation to the subgroup, then H and AH have the same order. They have the same size as sets. And what this says is, by transitivity, all the cosets have the same size, because any other coset BH will also have the same size as H, which also have the same size as AH. So they all have the same size, okay? So the way we prove that two sets have the same size is we exhibit a bijection between them. We show there's a one-to-one and onto function between the two sets, and here it is. I'm just going to prove it by giving you the bijection. So define a function f that runs from H to the coset AH by taking an element little h of H and mapping it to A times H. And remember through the whole argument here that A is a constant. A is a constant. So clearly by definition this has the correct domain and codomain. And it's also clear that it's onto. So if you take any element of the codomain, an element here looks like a little a, which is a constant, times a little h, which is somebody in H. So that same little h will be the element back in H that will hit it. So f of H is AH, and that hits it. So you're done. So it's certainly onto. To see that it's one-to-one, suppose you had two elements from H, call it H1 and H2, and those two elements end up mapping to the same element in that coset. Well, f of H1 is AH1, f of H2 is AH2, and those are equal. But that's an equation inside my group G. And the group G has left cancellation, so I can left cancel the A's and learn that H1 is H2, and therefore H is one-to-one. So we're done. That's your bijection. So we're finished. It's that simple. It comes down to left cancellation in the group. Thus we learn that the coset AH has the same order as the subgroup H. Right? So when H is finite, this just comes down to literally counting the number of things in H and the number of things in the coset AH and seeing that they're equal. But this is even correct in the infinite case, as long as you interpret infinite cardinals correctly. Just a really basic way to think about it is, if H is infinite, then so are all of its cosets. But it even goes finer than that. It even respects the different infinities that we get from different infinite cardinals. Don't sweat that too much right now. Now, it should be clear there's nothing special about left cosets here, and everything works on the right-hand side as well, so that every right coset has the same order as the subgroup H. And it's true, and it's almost the same proof. And so what you learned is that, well, every left coset has the same size as H, and every right coset has the same size as H, and therefore by transitivity every left coset has the same size as every right coset. Now in the last handout you notice that the left and right cosets, they can be different, and that's okay, but the point is, even when they're different, they have the same size. So the next result is even bigger. It claims something different. It says that, well, not only do the individual cosets have the same size, right, whether or not you're working left or right, it's also true that the number of cosets agrees when you work left or right. Okay? Again, this is even true in the infinite case. So let's prove it. So what we're going to do is form a set script L, which is a set of all left cosets. So now a coset AH is an element of this set. And similarly, let R be the set of all the right cosets. And when I say all the cosets, I mean all the distinct ones, no repeats. I claim that they are the same in size, so the number of left cosets is the same as the number of right cosets. And I prove that with, again, giving a bijection. Okay? So proposition 2 claims that there is a one-to-one and onto correspondence between the set of right cosets and the set of left cosets. And I define it this way. To take a right coset hx, I map it to the left coset x inverse h. Okay? Now I'm not going to run through the proof because you can read this. The proof is going to use everything that you know from proposition 1 in the previous handout. How do you work with cosets? So I do want to point out the first problem is there's a big question with this function even being well defined, because this function is defined on this coset by selecting an x that represents it. And that x that you select to represents it is used to calculate the image. But as we know, any coset has multiple representatives. So how do you know that if you picked a different representative for the same coset that you're going to get the same output? That's the question of this function being well defined. So the question is it possible that two right cosets are equal, yet their images are wrong, they're different? If so, that's bad. I'm going to show that cannot happen. If you suppose that HA is HB, what that means in working with right cosets is that AB inverse lives in H because we're right cosets, so the inverse is on the right. And then you use that to prove that f of HA is actually going to agree with f of HB, and so we're well defined. After that, you check that it's one-to-one and onto, and I give the argument here. Okay, so read that. If you have questions about the argument, post it to the discussion board or ask me in office hours. So this leads us to a very important definition. This is definition 1 on this handout. Let H be a subgroup of the group G. The index of H and G, so I'm defining the term index, and it's written this way: hard bracket G colon H close the hard bracket, is the order of the set of left cosets. Okay, just how many cosets there are. Now, of course, since we know there are as many left cosets as there are right cosets, some people define this to be the order of the set of right cosets, and of course, it makes no difference. We just proved it's the same. Okay. Now, all this is simpler when the parent group is finite, because when the parent group is finite, H itself has to be finite, and then the index of G colon H is simply the number of left cosets, how many cosets you have. That's it. That's it. So let's look at some examples. Example 1, let G be Z mod 12 and let H be the subgroup generated by 4, which is 0, 4, and 8. We've done this before. We did this in class before we adjourned. The left cosets of H and G are these 4 different cosets. Okay? And since there are 4 different cosets, that means the index of H and G is 4. Right? So the index of H and G is 4. Note that every coset has 3 elements, and that's exactly the same as the number of elements in H. We proved that in proposition 1. And here's what you got to notice. Note that the size of the parent group, 12, is equal to the order of the subgroup times its index, right? The order of the parent group is the order of the subgroup times the index. 12 is 3 times 4. That's what we noticed before we adjourned. I'll let you read the rest of the examples yourself. Here's an example with Z mod 30 and this little subgroup generated by 5, okay, which has 1, 2, 3, 4, 5, 6 elements and 5 cosets. So the index is 5. You can read the rest. Here's a dihedral example. Let's do some non-abelian examples. Here's a symmetric example. Here's an example in S3. And just for fun, for no good reason, I did it with right cosets. Of course, it doesn't matter. The numbers are the same, although the cosets might be different. So your 2 exercises for this handout for the Canvas quiz is to do the same analysis I just did with G being S3 and H being the cyclic subgroup generated by sigma 4. Work out how big sigma 4 is, work out the index. Do the same thing for letting G be Z20 and H being the subgroup that 16 generates. Find how big 16 is and find the index of H and G. Okay, so finally, one little warning. All of this works with infinite groups. You just have to be really, really careful. The one big mistake people make is assuming that if G is infinite, then all of its subgroups are infinite. That's false. That's false. It is possible that H could still be finite. In this case, the index has to be infinite. Think about why that is. Okay? However, if G is infinite and H is also infinite, it is possible the index could be finite or infinite. This gets a little bit complicated. The bottom line is don't assume too much about infinite groups. We'll have a homework problem later that gets into this, okay? For now, a little example I think suffices. Here's an old example you already know. Let G be the integers and let H be the multiples of 4, so the subgroup 4Z. That's infinite. So in this case, they're both infinite. But there's only 4 cosets, right? So here's a case where the index is finite, even though the size of G and the size of H were both infinite. Okay, so think about this. Try this stuff out, see how it goes, and let me know if you have any questions. Bye.